We'll welcome our next speaker now, Professor Hanna Kurniawati. She's a professor at the School of Computing at the Australian National University. You can go ahead. And the SmartSat CRC Professorial Chair for System Autonomy, Intelligence, and Decision Making. Her research interests span planning under uncertainty, robotics, robot motion planning, integrated planning and learning, and computational geometry applications. Specifically, she focuses on algorithms to enable robust decision theory to become practical software with applications in robotics and the assurance of autonomous systems. Help me welcome Hanna.
Was working before.
I know. Maybe click out of this. Oh, here we are.
Okay.
All right.
Okay. Thank you. Thank you so much, Ken, and thank you so much for inviting me here and also for organizing this this workshop. So I'm going to talk about some of the issue on curse of history, or in terms of how we handle long horizon problems, in particular when we want to account for uncertainty a bit more explicitly. So perhaps I don't think I need to talk about the need for general purpose methods in this crowd, but I thought just because it seems interesting that when we talk about task and motion planning, usually what comes to mind is more on robot manipulation, the task and motion planning with respect to manipulation tasks. But I found somewhat recently that there's actually somewhat similar problems as well in this type of helicopter emergency medical services, in particular on the developing the co-pilot for this. So basically, in this kind of problems, we actually want to help pilots. So the one who will navigate the robot or the helicopter is actually the pilot and not an autonomous system. But we want an autonomous system to help the pilot to figure out what kind of mission, in the sense that who should they pick up, which victim to go next, what kind of route should they take? Should they pick the victim and go all the way to the hospital, or perhaps different possibilities and combination depending on the conditions of the person? So it has flavors of the task and motion planning because we need to consider the different possibilities on the victim's conditions, the different possibilities on how far it is to get to the destination, and so on. And in the same time, we need to consider the underlying motion planning on how to get there safely and, well, hopefully, while the person is still, there's enough time to save the person. And so this is just a motivation to say that we actually need quite a general purpose methods, and in particular, perhaps when we want to look into these two different problems, the types of uncertainty that we need to handle are also quite different, but the kind of problems from the decision-making side of the robot is actually somewhat similar, which is that what's the strategy that the robot, or in this particular co-pilot-based system, is what kind of recommendation should we provide so that we can get good long-term outcomes despite various types of uncertainty. So we want to be able to have a general methods that can handle uncertainty in these various different scenarios. And so the general purpose framework for handling uncertainty is the partially observed Markov decision processes, and that's what I've been working on, and that's sort of what I'm going to talk about in the rest of my talk here. And so POMDP is nothing more than mapping from observations to actions. It's just that we want to be able to account explicitly for uncertainties, errors in perception and in the sensors measurements, and also uncertainty in the effects of actions, be it because of disturbances, because not knowing the exact characteristics of the objects we are working on, for instance. And of course, we want to have some kind of objective in which, in this case, is derived from the reward functions. And in this mapping, we essentially just run somewhat similar to feedback loop, right? So we estimate the states, and then based on that estimates, we choose what's the right action to perform so that we can get good long-term return. The only thing is that when we do this state estimation, we actually take into account that, well, we don't actually know the exact states. So rather than saying we assume that it must be in this particular most likely state, we basically say, well, it's, we account for distribution over the state space, which usually is called as beliefs. So then the best action we select will be with respect to this distribution of our beliefs. And this is, sorry, distribution of our state space. And this is exactly where many of the difficulties comes in terms of the computational complexity. Because now I don't even know which state I might be in. There's many possibilities, and I need to consider the possible futures if I perform certain actions and get certain observations, right? And the problem with many of these tasks and motion planning problems is that we need to consider many steps in the future before we can see whether it's actually beneficial or not, for instance. And that's where the long horizon issues come in as well, or in the POMDP context, usually it's called as the curse of history, just because the complexity actually grows exponentially with the number of look-ahead steps that we need. Okay, so in terms of the objective function, it's really that we just have two components. One is the simple to compute, which is just the immediate reward. The second one here is the difficult part to compute, because we need to consider the future possibilities that grows exponentially with the number of steps we want to consider. And so for theoretically, solving this is computationally intractable, but we have seen quite a lot of advances over the years. And so we started perhaps like in the 2003, even solving this kind of 3x4 grid problems took days, and perhaps not such a good result. And we see how sampling base actually have made this possible to solve much larger problem. This is sort of one of the breakthrough in 2003, where we start solving target finding problems with 870 states. So it still takes a long time. And then it moves on from there. We can start solving much bigger problem. And also there's a lot of work on applying this to more interesting problems later on, from the study of collision avoidance of aircraft to picking up small objects in non-prehensile manipulation to human-robot collaboration. And also this is from my lab, so this is actually about trying to uncover how honeybees avoid collisions in collaboration with some of our biologist colleagues. And so in here, we actually use POMDPs to accentuate data. And this is just sort of giving a range of different flavors and different types of applications on showing the generality of this kind of methods, and sort of this where it can and it has been applied so far. So there's, of course, there's many problems that we need to solve. This is just coming from my labs, and we are by far not the only group that are doing this. And many of them are sampling based in terms of the advances that has been made, but more recently we have many of the learning based methods as well. For the sampling based, perhaps just a little bit of an advert, we try to understand what's the insights behind it, and we summarize this here. And what I want to talk a little bit more about this curse of history or the long horizon problem is that in many of the approaches for handling long horizon problems, we either do better abstraction, so for instance, like HTN that has just been mentioned, right? Or we actually try to generate macro actions, which is another way of looking abstraction as well, but abstraction in the action space, right? And there's different ways of generating these macro actions. The most recent one is trying to generate this using learning methods, which has been quite successful as well. But in this talk, I'm going to try to look into a slightly different way of handling this long horizon problem, which is that to look into the primitive components of computation. So primitive computation is actually not foreign for anyone working in motion planning, in task motion planning, right? So the scalability that sampling-based motion planning has made, for instance, from Lydia's lab, started from her lab, is actually also to a large extent because we have a very fast primitive, which is a collision checker, right? And if we then move on to this planning under uncertainty, task motion planning under uncertainty, then the primitive computations that we want to look into there are primitive computations as well. And I'm going to talk about sort of two distinct approaches for this solving of POMDPs and how the primitive components actually help in both of those cases. So one is pure planning based, the other, at the other end of the spectrum is pure end-to-end learning. So in terms of the pure planning base, so we started by looking into if we want to have this POMDP applied to more realistic task motion planning, in many cases, the state dynamics, so the transition that needs to be handled are somewhat complex in the sense that it's not actually a closed form solution and computing them can be quite expensive. And so, but that part is actually called many times and can be quite a bottleneck. So this is just an example on how much time are being done for dynamic computation per planning step. If we use the typical benchmark of POMDPs, which in this case is actually drawn from the what's called the rock sample problem, essentially nothing more than a robot that needs to figure out which rocks to sample, given that it doesn't know which one is useful and which one is not. This is useful, for instance, in space exploration type of problems. The other one here is if we want to do force control in this 7 degrees of freedom robot. So the dynamics computation being spent in here, this dynamic computation basically is simulating the transition per step. And the total number of those, the total time spent in those computations for this one is really less than 10%. And if we start looking into this more complex problem, it actually spans almost 90%. Right? Which means that if we can somehow reduce this time for dynamic computation, per dynamic computation, then we can gain a lot when we apply to these more complex problems. And so where does this dynamic computation actually comes in? So if we just go back to that objective function in the beginning, essentially we are saying we want to have good long-term return, right? And that good long-term return actually is computed based on sort of an expectation of what might happen in the future based on our understanding of uncertainty in the effects of actions and also uncertainty in perception and sensing. And if we open this up, that's basically this component here where we need to forward simulate the states. And this actually requires us to compute what's the next state is based on that dynamics computation we do. So that particular component. And it turns out that if we can somehow, it turns out we can actually not use the original dynamics equation, and we can use a much lower fidelity, combine that sparsely with the expensive high fidelity dynamic computation, and for the purpose of POMDP planning, that seems to be good enough for us to get a good and reasonable strategy. And this can be applied to various different offline, online POMDP solvers that's available out there. because all of them basically rely on this sampling strategy, which is nothing more than doing a forward simulation based on samples of the beliefs, and then performing forward simulation based on the action selected, observations that are being sampled, and then looking into what might be the next state, and so on and so forth. So that's exactly what we did here, is that we borrow the concept from the multi-level Monte Carlo approach, which is that we can now vary the degree of fidelity that the dynamics computation we need to compute. And some of them are very expensive, which is the original one, and some of them can be very, very cheap, right? And there's a range of them. But the only thing is that we need to just make sure that these samples are correlated. Samples between the different fidelity levels are correlated. And how do we do that? Sorry, this is just from the multi-level Monte Carlo. The correlation comes because in order for us to estimate this, now we need to have this with respect to the difference between the fidelity levels. So we just need to make sure that correlation are there in our sampling-based methods as well. And it turns out we can do that quite easily. So we just, in order for us to sample the beliefs, as usual, we sample actions, and then we forward simulate. And all we do in here is that we do a forward simulation based on the quartz level of fidelity, so very fast, right, very cheap. But then after that, we sample the levels of fidelity we want to use. And once we sample that level of fidelity, then we again do a forward simulation using that particular level of fidelity and one level above it, and that's it. And it turns out we can do this quite fast just because we can reduce the single dynamic computation in many cases, into a much cheaper computation. Perhaps I just go to the results. So we are comparing this with the original software we built this on, and also one of the state-of-the-art, which is POMCP. And these are using 1 second to 5 second planning time per step. And the results of the overall performance improvement can be quite substantial just because of that single simple computation that we change. So that's the effect of changing the primitive computation into something that hopefully is better, because it is called many times, and so that resulted in much better overall performance. And so this is, we try to see what happened as the planning time we provided are increasing, and we can see that we are actually reaching quite a high level of performance, even just with 1 second planning time, whereas the other methods requires quite a bit longer time to converge there. Okay, so that's one part, which is actually pure planning based. So now, once we move to the end-to-end learning, it turns out that we can also figure out that we can construct a very simple module that does a better job in doing a forward forward propagation of information, and that results in a significant improvement as well. So, and this is actually the work of Nick Collins. He's about to graduate, so he's going to be on the job market very soon. So I'm advertising that for him as well. So anyway, so in this case, with the end-to-end learning in POMDP, usually the problem is that because we also don't have the POMDP model. So what that means is that we don't have the transition, observation, and reward function. And all of these are being learned together with the solving. So this is sort of from the literature. I'm going to give this overview for the simpler version of POMDP, which is the Markov decision process, where the state space are fully observed. So it's, in this case, I don't work with beliefs, but with the states, because it's fully observed, right? And so in here, we can actually represent this as a convolution where the transition is the weights that we are going to learn. So we are learning this transition function. And then we are going to sum this. This is, again, nothing more than just a summation in a convolution neural net. And this reward part is something that we are going to learn as well. And the maximization is nothing more than just a max pool. And this is value iteration, so we need to iterate this over quite a number of steps. And what happened is that we just represent this as a recurrent neural net. Its iteration basically corresponds to a single layer. And this is essentially the idea of the value iteration network that was proposed back in 2016. And it has been since expanded to the belief version, so to the partially observed Markov decision process, by incorporating basically a neural net representation of bias filter so that we can now work with beliefs as well. That's the work of QMDPNet. Sorry, it gets cut below, but that's there. So now, going back, so what's the forward propagation primitive in there? So if we go back to this MDP objective function, basically this particular component that we say this is nothing more than a convolution. Oops. So this is basically propagating information from the current estimated value function that we have computed to the next step in the value iteration step. Right? So that's the forward propagation primitive here. When we talk about the POMDP, it becomes a little bit more involved, but it's also that we actually use this forward propagation primitive in more than just one place. So if we improve this, there's actually going to be more benefit as well. So, this is now this B is just a beliefs. And the forward propagation really is looking into what's the value of the next beliefs given the action and the observation it has performed and perceived. And this part here is basically the forward propagation primitive, forwarding the information about the current computed estimated of the value of the beliefs to the next step after the iteration. And the other part is also used in the bias filter when we try to estimate the beliefs itself. So basically, that two parts. And what we propose is this very simple module to do this forward propagation primitive a little bit more efficient. And the key to that efficiency is really nothing more than saying, well, the transition function actually is quite local, at least for many robot motion planning problems. Right? So I don't expect if a robot has errors in its movement and it is now here, I don't expect it suddenly jump into Australia. It's a bit too far. Right? So it's great, but it's not going to happen. And so that's the representation we try to impose in this simple forward propagation primitive module. And so this DS is really what's the change in the states that is happening after a particular action is performed. So it's no longer what's the next state, but it's just what's the change of states that's happening. And so it turns out that if we do that, because it's being used repeatedly, we can gain a lot. So this is the details of the architecture. I think I'll skip that. So where it is going to be used is that this entire thing here is basically the value iteration network. So we just embed this small module in between iterations of the value iteration network. And similarly, this part for the POMDP part is actually the belief estimation. And this is used to forward propagate beliefs in here. So when I say forward propagation of information, it can be for propagating information about beliefs or about value functions. So in here, it's about forward propagating beliefs. And we just put this additional small module again in here. This is the use of bias filter that's represented as neural net. So just by adding those two modules, then we can gain quite an improvement. So in here, we are actually training this problem of navigation in this kind of environment with a much smaller grid world. So it's really just 16 by 16 navigation grid world that we are training on. So what that means is that the memory that we require for training can be much smaller. The time that we require for training will also be smaller. And this is if we just run the value iteration network without that additional module. This is if we add the additional module. And if we run this on the POMDP version, because it's being used in multiple different places, we gain even further improvement. If we do dynamic environment, we can also gain some improvement, and we can also see that the training time is reduced. We also have some example on the grasping problems in the paper, but I don't show it here. But the main thing here is just that, so it turns out even in the end-to-end learning, which usually sort of doesn't talk much about the primitive computation that are being used over and over again, we can actually develop this very simple module that is being used many times. And if we improve that, then we can gain quite a bit. And so that's all that I want to say. All I wanted to say is that when we talk about long planning horizon, all the work with hierarchical abstraction, with macro actions, all of them are definitely beneficial and great, but perhaps we shouldn't forget as well that there are these primitive components that we can improve, and maybe that improvement can help a lot in the overall performance of the system. And that's it.
Questions, please come up. I'll start with a question, and I don't want you to elaborate too much because I want to save it for the panel, but if you can just give a little bit. So this model that you described, the POMDP model or MDP, is very different than everything that we discussed about previously.
Yeah.
So how do you place this model in comparison to the TAMP model that we introduced previously?
So I wouldn't say very different. It's in the sense that, let me just go back to the model that I put it. Yeah. So the only key is that in many of the TAMP model, we don't explicitly represent the uncertainty as distribution. So in the TAMP model, in the motion planning, we still have the forward simulation. That's the whole point of planning, is we need to have forward simulation. That's represented in this transition function. It's just that now the transition function is actually in a probabilistic form, conditional probability function, rather than just a deterministic one. So in addition to that, in many of the TAMP model, we assume that the problem is fully observable. And so the assumption is that if we get this observation, or we might even assume that we know ahead of time, right? So in here, well, our observation function is not actually perfect. And so again, we represent this as conditional probability function. But that in the TAMP model, we can think of this as an identity function. So there's actually, I can say that this is a more general model of the TAMP model, if I may say that, without causing issues.
You may say whatever you want. It's up for discussion. It's up for discussion. Anyone else wants to come up for questions? All right, so let's thank our speaker again. So now we're going to switch.